Okay, welcome back. So here is a reminder on two things that happened last time. So basically we started with the Planar Ising model, and then there was the first part of the lecture, which was about how to represent the Planar Ising model through dimers. Well, there are several variants, but actually I discussed only this one. And then it was the second half of the lecture, where I introduced another formalism, which is called spin disorder operators of Kadanoff and Seva. And based upon questions you're asking, okay, this is more complicated and this is normal. I mean, the fact that you are not that, how to say, that this is a bit nasty for you, that's fine. But still, I'm going to use this formalism, so yeah. That's exactly the purpose of the first exercise sheet. What I'm going to do today is to discuss how to discuss this formalism, how to use these formalisms to compute things. Because after all, this is a school in integrable probability. So integrable means we can analyze the model. So you should view this stuff as a tool. But before doing so, what I want to say a word about is how are they linked with each other. Just to give you one identity. I already mentioned this identity in words at the very end of the first lecture, but okay, nevertheless, let us discuss this a bit, how to link between dimers and spin disorders. Remember, in the dimer story, the base point is to find the Castellane orientation of this graph. So once an orientation is found, then the partition function is just the Pfeffern. Probability to see concrete dimer is just the entry of the inverse matrix, and so on and so forth. So the question is, okay, is there any natural way to orient such a graph? I don't know, well, I don't like to say canonical because there is no canonical one, but somehow can we construct a Castellane orientation of such a graph? And here is an answer. So how to construct Castellane orientation of this graph? I'm just going to give you a recipe. So what is a recipe? Remember the vertices of this graph. They are in a one-to-one correspondence with both corners of the original graph, like that, like this C, and oriented edges of the original graph, like that E. So there are entries of three types, and I'm going to specify them. So before specifying what I want to do, I want to do the following. So remember, it was this eta C here, which lived on a complicated double cover, blah, blah, blah. Okay, now what I want to do, I want to fix a section of this double cover. In down-to-earth terms, just for every corner C, I fix the value of the square root here. I just choose one of the two possible values. So, okay, fix for each corner C. Fix omega C, and do the same with oriented edges. For each oriented edge, fix, well, exactly the same expression, where instead of v minus u, I use the direction of the edge itself. And the prefactor, yet again, don't pay much attention to this prefactor right now. Okay, so I consider E as a complex number. So this is, well, this vector I consider as a complex number. It has an argument, and I take the square root. And then what is the recipe? So first, say when I have two corners here, an edge between connecting two corners. Then I define a matrix. And this matrix, right now, this is still not a Castellane matrix. So Castellane matrix must be real antisymmetric, and this matrix is going to be just self-adjoint. So how do I define it? Given two corners, I just say, okay, here is a small picture, maybe. So here was my graph, my original Ising graph, and here there are two corners. What I measure, this is C prime. What I measure is just the rotation angle when I go from here to there. Okay, right, that's some angle on this picture. So, and what I declare is that this is by definition, wait a second, what is this by definition? This is just exponential of the square root of this rotation angle. And rotation angle, by some tradition, I denote by this wind, which actually is shorthand of winding, because for some reason people use the terminology winding. I believe it was Stas Smirnov who started using this terminology, and now it is standard. So yet again, this is just on the picture, this is just this angle. I turned left a bit, okay? Saying there. So this is the entry between C and C prime, and all the others, all the other entries are basically given by similar expressions. So if I need an entry, say, between C and E, well, they're barely distinguishable, then what I do exactly the same. Exponential widen angle CE. If I just have a long diameter between E and E bar, then this is XE, because it should be without any further thing. Question? No, that's yeah, that's a good question. Nope. In principle, nope. So I identified the corner with just the segment between the vertex and the face. So what I do, I fix position of faces of the dual graph. So I consider my graph again embedded together with its dual. Okay? Yeah, good question. Thanks for asking. Though in principle, here it is even irrelevant. So you can do whatever you wish, just draw whatever decoration you wish. I mean, for science, it is irrelevant. It will work anyway. So here is definition. I didn't tell you what is the entry FEC, but it is reconstructed by self-adjointness condition. So this is already self-adjoint. If you switch C and C prime, then this rotation angle, well, changes to minus the same angle, and there it's self-adjoint. This is just, you start from C, and you measure this hand. I mean, the rotation you do when you go from a, oh, that's C prime, this is C. When you go from C to E. Yeah, to the edge E. E is an oriented edge, oriented. Okay, so that's just, you drive your car, and you rotate by some angle. And the square root here can be taken canonically just because this rotation angle is always in minus pi pi. So there is no ambiguity in this definition. Okay? So all these angles, they are always in minus pi pi. So this is a self-adjoint matrix which is defined canonically. The only problem is that what we need in the Castellane theory is not a self-adjoint, rather an antisymmetric matrix. And to produce an antisymmetric matrix out of F, what I do, I use these non-canonical choices of half angles. So claim, so I use notation U, I'm going to comment, was that this is simply the diagonal matrix. Claim, this is the Castellane matrix, well, one of the possible Castellane orientations for the Fisher graph, for the graph F. So claim, this is an antisymmetric matrix. What is U? U is simply the diagonal matrix of etas. Just an exercise to check. Well, these complex phases, they match so that the entries are real valued. And the antisymmetry condition comes exactly from the fact that f is self-adjoint, and here there is I in front. Okay, this is not of great importance, this exercise, to check that this is the Castellanian orientation. What is of more importance is that this provides an exact identity between correlations one can obtain on the left and correlations one can obtain on the right. I'm going to write down this identity. Before I'm doing this, is there a question on what is written here? Yeah? U is just a diagonal matrix composed out of etas. Okay, so for every C and for every E, I have my eta defined. So this is just multiplication of that by eta and by eta bar. Okay. This just the same expression with the direction of this oriented edge instead of v minus u. So this is something which is defined purely geometrically. And this I over 2, okay, this has to do, I mean, with when you compute rotation angle, well, okay, this is exactly what produces you the real answer. Other questions? So to formulate this identity, I mean, to be on the safe side, what I'm going to do, I'm going to slightly change the weights of the dimer model, and this is an important thing when you work with the dimer model. Actually, given a graph, weighted graph, you can multiply, and the vertex of this graph, you can multiply all the weights of edges incident to this vertex by a number, and the model doesn't change. So what I'm going to do, I'm going to replace this x by 1, this 1 by x minus 1/2, and this by x minus 1/2. And similarly everywhere else. So I just multiplied every weight of an edge incident to this vertex by x minus 1/2. Why here is 1? Because there are two edges there. Just a second. Yep. Question? Yep. Because the graph F, it actually has vertices of 2 types, corners and oriented edges of the original graph. Okay. Take a look on the definition page. There is this bijection. So the original Ising graph, it was here. And similarly, what I do, so here I replace this by 1, and I multiply this by minus 1/2. Yet again, from the dimer model perspective, this is a trivial operation because such a multiplication doesn't change the probability measure on the set of perfect matchings. So it is just to eliminate unnecessary factors there. And here is the claim. The entries, if I think only about, let it be D, only about those entries labeled by corners, then this is exactly as the expectation psi C, psi D. Well, okay, almost. So 2 comments. First, what is the complex phase of this quantity? Chi was real, so basically this is eta C, eta D. And what is the complex phase of this quantity? Okay, here it was U and U bar. And because of that, it should be either eta C, eta D bar, or other way around. So one of the eta C's is present itself, and the other is complex conjugate. So with a small correction, which I have somewhere, and of course I never remember what this correction is. So this correction is probably I eta D squared. Yet again, the only point is that this is something very, very concrete. And there is no ambiguity in this quantity. So now there is no ambiguity neither here nor there. That's okay. And another another thing to mention is that still this is not always true, provided that the corners are incident to distinct vertices. Okay. This is really relatively, well, not long, but okay, some medium-sized story short. The message is that dimer correlations, they can be recovered from these correlations. So the formalism on the right is more powerful than the formalism on the left. So it includes simultaneously all the dimer correlations when some signs are twisted. Remember these pictures with double colors and so on and so forth. What is not at all obvious from this formalism is there is a Pfaffian structure behind. So because on the left, I can play with minors of f. And this should recover me expectations of psi C1, psi C2, psi C3, psi C4. And it should be Pfaffian identity between them. So this is also true, not at all clear from the formalism itself, but just to formulate it explicitly. All the correlations on the left, they can be recovered from the correlations on the right just by this coupling procedure of spins and disorders. And the very last comment, to which I'm going to come back maybe at the very end of this lecture, is that the formalism on the right hand, it is fully symmetric. It doesn't distinguish vertices and faces. It is self-dual, as discussed in the exercises. So if I replace the graph by its dual and vice versa, then this formalism is self-dual. This picture is not self-dual. This is in particular, okay, the reason why here the fact that V and V are distant is required, but the fact that U and U are distant is not required. Okay, so this is not that self-dual. It might be inconvenient in some situations. Okay, and so that's what's about the link between dimers and spin disorders. And now I move to the main goal of today's lecture. And the main goal is how to use all that. So you developed some combinatorical nonsense, or maybe some sense even in that, but how to use it for computations. And the first setup to discuss is just the regular square grid. So the combinatorial formalism, it is always there. So now we want to compute things. We should specify some concrete problem. And now what I'm going to discuss, is the phase transition on Z2. Homogeneous model, which means that all the interaction constants corresponding to edges, they're all the same, say 1. An important remark, if I think about a dual model, the dual grid is also Z2. And all these expressions, okay, they make sense both in the original model and in the dual. I'm going to comment on that. Okay, when we work on an infinite graph, we should say something about Gibbs measures. I believe that most of you have heard, well, something about at least one model of statistical physics, and this is always a story at the very beginning of the Gibbs measures. I'm going to take this story for granted. So what I'm going to say is that, okay, for granted, how the picture does look like in this situation, okay, on every reasonable, say, periodic grid. There is one parameter, which is beta, which is inverse temperature. Then for small temperatures, which means large betas, there are two extremal Gibbs measures. those who come from either plus boundary conditions, as I discussed in my final graphs, or minus boundary conditions. In particular, if I start with free boundary conditions and then enlarge my domain, what I have is just a linear combination of these two measures with the weights 1/2, 1/2. And above this critical temperature, so this is small temperature, this is big temperature. There is only one extremal measure, one Gibbs measure. So this I'm not going to discuss because the question is how to do computations. So just let us take this for granted. What is of importance is that they are always translationally invariant. Translationally invariant. And in particular, if I'm thinking about products of an even number of spins, this is always a well-defined quantity, because if I have even number of spins, then the product is invariant under this flip of all the spins. So when I simultaneously change all the variables by minus them, okay, the product doesn't change. So expectations of in the full plane are well defined. This is what I need. In principle, the most interesting statement here is that there is only one phase transition in this picture. Okay, let us take this for granted. Now, what do I want to start with? First, I want to say that we already know actually what is the value of beta. So the first point is, okay, how to guess beta critic. And this is due to Kramer's idea. Very old idea. So remember that we had two ways to interpret the same quantity, either on the original lattice or on the dual lattice. And it was such notation, so we do not have any G. Okay, under this interpretation, we had this identity. And this is, in fact, an involution. So this is equivalent to say that hyperbolic tangent of beta is exponential minus 2 beta star. Trivial exercise. Let me denote this by X prime. So this is an involution. And of course, if we believe that there is only a single value of beta, which is special, then it must be the fixed point of this involution. And this is square root of 2 minus 1, which, by the way, is tangent of pi over 8, just a fact. And this is for something. I'm going to explain why this is of importance and that is not. I mean, the square root of 2 minus 1 is just a value, and tangent pi over 8, this is a meaningful statement. So to explain this, I'm going to use, from now onwards, I want to use this parameterization. So each time I have a weight per edge x, I define theta to be twice our tangent, inverse tangent of x. Okay? So this is definition of thetas. And actually, this involution in in exponentials, it reads simply as theta plus theta star equals pi over 2 on the left side. So that's, again, some straightforward exercise. So it should be translatable to this language of thetas, so you can get, it should be possible to compute. And here is an answer. Okay? So later on, we will see that this pi over 4 for each of them, it actually has a geometric meaning, but not right now. Okay, so right now, this is just a notation. Okay, it's notation. And coming back to the phase transition, the message here is that we actually can guess what is the critical value. Now, if we, any question on this? Just some, I don't know, explicit, yeah, quite trivial, in fact, expressions. So what I want, I want that the model with the weight per edge x, okay, if I assume that, what I want to say is the following. If I assume that the model with the weight per edge x is special, then because of this duality, the model with the weight per edge x star is also special. If somebody tells me that the special value is unique, then it necessarily implies it must be the same, which is an equation, quadratic equation on x that I can solve, which I can solve, and that I can solve as well. So that's the logic. But right now, this is a guess. So that's guess. And if we want to compute something, okay, we should find a quantity of interest. So the actual quantity of interest will be just the product, expectation of the product of two spins. But before doing so, I want to mention easier quantity to analyze. So easier quantity to analyze, what you typically see in textbooks, is a free energy per side. I'm just going to hand wave how one can compute this quantity. So if you never heard what is that, change the blackbirds. If you never heard what is that, just a definition. Well, let us, instead of working in the full plane, let us consider the model on the torus. Here are some things that started to be put under the carpet, because I should specify what the boundary conditions are. But I'm not going into details of this computation anyway. Okay, so let us consider the model on the torus, compute the partition function. Then the principal behavior is that it grows like exponential of the volume of the torus. So this is on the torus. Say with periodic boundary conditions. And then what I'm interested in is what happens with this quantity when n becomes larger and larger. And there is a standard technique to do so, to compute this quantity, which is based upon the following fact. So after all, this is a dimer problem. And computing partition function of the dimer model is just computing pfeffens. Well, it's slightly more complicated here because because now my pi 1 is not trivial. So it would be not one pfeffen, but a sum of 4 pfeffens. But okay, let me do not comment on that. So this is computing a pfeffen of a matrix. And this matrix can be done periodic, actually. So to construct this matrix, what I need is a orientation, is a Castellan orientation of my graph. And it can be done periodic, in particular by this concrete, for instance, by this concrete algorithm. So if I make these arbitrary choices of etas in a periodic way, what I have is a periodic matrix to compute the partition function of the Dymir model. And okay, to compute the determinant of a periodic matrix, this is of a huge periodic matrix. This is a standard problem. You do Fourier transform. So the answer is like that. This is an integral over the unit torus. So what is FZW? So in the square lattice case, we have a very simple fundamental domain. So this is something like that. And the integral is over the unit torus. We have a very simple fundamental domain. So the weights of edges, they are the same inside of this domain. And what I change, I say that when an edge crosses this cut, I put variable z, okay, by the weight 1. When I go other way around, so this is this edge. So this edge is z. And when I go other way around, then I put 1 minus z. Red is not visible, right? Okay. Red is 1 over z. And I do the same in the other direction, so with w and 1 over w. So this is a very, very concrete small size matrix. So in this direction, I do w. And the other way around, 1 over w. This is a very, very concrete small size matrix. So this is absolutely explicit. Okay? Yet again, what is the reason for such a computation being possible is just the fact that we are computing a Pfaffian of a matrix which has a periodic structure. And because of that, you can guess, I mean, you can always play with Fourier transform. The matrix is exactly the matrix I have constructed. Yeah. And that's a very general statement. You can start with whatever Dymir model. So you organize such a matrix twisted by z and w. And then, okay, here is an answer. I'm not absolutely sure about the coefficient, but in any case, this is just a numerical coefficient. Okay. So now what happens is that how this critical value is specified, you can wonder what happens with this function when beta changes, when the temperature increases. So this function is not C2 at the critical temperature. As a function of x, it is analytic everywhere except at a single point. And analytic. And this is exactly what characterizes critical phenomena, that some quantity of interest in the system loses analyticity. Yeah. Say again. In this formula, no, there is this x. So x now is hidden in the adjacency matrix because this is an adjacency matrix of, I need another color, of a weighted graph. So x is still hidden here. So these edges, they have weight x minus 1/2 in this notation. Yet again, it might be not, I mean, it might be some arithmetic correction needed, but just to grasp the idea, okay, some explicit terms may maybe else related to this passage from 1 to, from the x here to 1 and x minus 1/2 there. But okay, the idea is that for periodic dimer model, one can compute this quantity just using periodicity by Fourier techniques. Okay. And yet again, that's a very general statement. So you can play with more complicated fundamental domains, more complicated graphs, and not a problem. Okay. In terms of this function, so this function now depends on this determinant, which is a real number. It now depends on x. So this is an algebraic curve, right, which depends because this is a polynomial in z and z minus 1 and w minus 1. It depends on x. So what happens is that below criticality, this curve doesn't intersect the unit torus. So when it changes, everything is analytic. Exactly at this point, it touches the unit torus at the point 1, 1, in fact. And then it shrinks back. So that's the reason why analyticity is lost exactly here. So that's a relatively standard thing to do in the classes on the Ising model. And what I want to do now is a less standard thing. So what I'm going to do now is to compute a two-point function. Just to compute okay, it happened that I have a picture, and you already saw that I have a picture there. So what I now do, I rotate my grid. For some reason, it's easier to work with the rotated grid. So this is still a square grid. And what I want to do, I want to compute the expectation of the product of two spins. Diagonal spin, spin, a distance to n, spin, spin correlation. A distance n. So n is just the number of, okay. N, well, let me say about what is the notation explicitly. So here, I assume that the picture is drawn so that this diagonal is of length 2. So this is 2. So that this corners is a sublattice of Z2. So these corners, they have integer coordinates. And there is another picture on the TA session 2 exercises, just more or less the same. So this to n is a Euclidean distance. And in terms of lattice steps, this is n lattice steps. Okay, well, misleading. N lattice steps. Distance n steps, and I'm going to call it dn. So dn depends on x, right? Just to remember. Okay. So let me try to do so, but I need some preliminaries before doing that. And preliminaries are as follows. So what will be my main technical tool? My main technical tool for such a computation will be the following function. I'm going to write it here. So using this formalism, what I'm going to do, I'm going to consider such a correlator. So I have one disorder, one spin, and another two coupled with each other. So this is a real valued quantity. So what is V and what is U? Here is V, here is U. And C is going to be just a corner of this type. I don't know how should I call it. East west corners, or east, depends on whether I see from vertices or from faces. Okay, so those things are going to be C's. So I want to think about such functions, and here is a very important idea. What I want to say is that these functions, they satisfy really nice identities. And in fact, this is the content of the first exercise sheet. So I'm going to comment on this, but not providing solutions. Okay. Let me say a word about identities. So identities for it's called propagation equation. For functions, well, going to use this notation. So what is what here? What is what here? This is also in the definition sheet. So what is that? I put a number of spins, a number of disorders, and one chi. Other way around. Here is m. Here is m. And this omega or calligraphic pi, in fact, this is just a collection of all the points. So this is the notation. There is nothing behind the idea that what I consider is a number of spins and disorders and only one pair is coupled. And I want to emphasize that I think about this function as a function of C. So in this concrete example, okay, V and U are fixed, C is moving. That's the idea. Okay. There is a claim. This is problem number 3, if I'm not mistaken. So each time you have such a picture, and that's a fairly abstract claim. You do not need any embedding of your graph. You do not need to assume that the graph is a square grid. Each time when you have a picture of this kind with 3 corners going consecutively along a single edge, so this is xe in the original graph, there is an identity xc2 equals xc1 cosine theta plus xc3 sine theta, where theta is exactly this parameterization. So this xe is tangent 1/2 theta. Okay. Just an abstract parameterization. So what I claim is that, yep, there is such a 3 terms identity. Warning, just wake up. What happens if I consider another corner? You might have an impression that if I write the same equation for this corner, I have exactly the same answer. And this sounds to be something really bad, because, okay, it shouldn't be the same quantity everywhere. So the catch is that these 3 corners must be consecutive on the double cover. So when I write an equation here, for the value of xc1, I should take the value on the other sheet of the double cover, which means that minus appears here. So that's the message. And again, an exercise is to check that everything is consistent with this double cover structure. It holds for every graph. This doesn't require any embedding even into the plane, so you can think about up to homeomorphism. Because definitions of these mu's and sigmas, it doesn't know anything about how the graph is embedded, except that you would prefer to keep it up to homeomorphisms. Okay? So that's topological notion of what is next to what. Okay. So here is a propagation equation, and this is an exercise to check. In particular, by the way, it justifies why this is a convenient parameterization. Okay, the equation is nice. Take definitions there, and it is on the second page. They are just here, like that. So, well, let me write on the blackboard, because I know that that's exactly the place where some of you have problems. So, okay, if I point here C4, let me take this C4, then what happens is that XC4 is XC2 cosine theta plus XC3 plus XC1 star, yep, am I writing this correctly, sine theta. And this XC1 star is X minus XC1. So this is really an equation on this crazy double cover. This poses a problem, because a crazy double cover is not a usual thing to think about. So you always have an intention, let me consider a section of it. Let me just choose a representative everywhere. But if you choose a representative, this leads to some more or less chaotic pluses and minuses here, which are even harder to control, rather than to think about this branching structure. So that's like a conundrum. There is no easy way. Either you think about the canonical double cover, or you have some arbitrary choice of signs that you always need to control, and this leads to nowhere as well. Okay, so here is a propagation equation. But what I want to say, what I already said even, is that I'm interested in my functions only on this type of corners. And there is a claim which I'm not going to prove, so I just want to indicate that, okay, it should be possible to justify this claim by very straightforward and stupid computations. So there is a corollary. Imagine I have such a picture. So I have a corner of this type and 4 corners nearby. I need some notation. Let it be something like that. Just 4 neighbors. And I wonder is there a way to express this value in terms of those values? And the answer is yes. So let me write it first, and then we discuss what exactly it means. And I can put here whatever the double cover I wish. So the message is that actually some very, very familiar appears. So still there are comments to make, but just a general message is that something very, very familiar to to everybody appears. But look, this is something about random walks, right? What is M? What is the notation? I'm going to comment. Okay, so where M is just sine to theta in my situation. So for that, what I assumed that all xe are the same. So I really have combinatorics like that, and all the interactions are the same. So here is what is the value of M. Just to indicate how one should prove such identity. Well, okay, it's a stupid game, so you have some linear equations relating triples of them, and there is a way to eliminate everything except this 5. So you play with this identity, with this identity, with this identity, this identity, that identity, this one, and so on and so forth. This one and this one. And I believe that's it. If there are 8, it should be fine. So every green wedge means that I take 3 terms identity of the kind written above. And what I claim is that the proper linear combination of those gives exactly that. And there is a very last comment to make. So right now, is it at least the type of the statement clear that I'm making? So what I said is that there are identities relating, linear identities relating triples of values. And now what I'm saying is that there is a way to combine 8 of them so that something really nice appears, and we can almost forget about all these crazy things with double covers. Okay, almost. Because the very last remark to make is, okay, but what is the choice of these C's, right? A priori, the alpha should live on this crazy double cover thing. And good news, guys. So here there is no problem. So there is a simultaneous choice of C's of a given type at every sheet, at every position, such that, okay, this holds. So this holds, just there is a non-branching section of this on this type, this fixed, on the fixed type of converse. And the very, very last thing to say, provided there are no another branchings nearby, provided that we are far away from these 2 points, far away of points. Branchings. What I suggest is to think about this concrete example. In this concrete example, what the story boils down to is that now there is really a function of the type like square root of z minus v, z minus u. So it is defined just on this grid, and it changes the sign when we go around here or around there. And the equation is the simplest, is the simplest for probabilities. This is just massive harmonicity or random walks with scaling. And yet again, this fixes the phase transition point clearly. So at the critical point, where is it? Here. What appears is exactly discrete harmonicity condition. This is the message. Okay? So this M is exactly 1. So you have discrete average property. Okay, let me keep this blackboard, but erase that one. But still, yeah, I promised to compute things. I mean, to compute this dn. So how to do that? And the result itself is very, very classical and very, very old. It dates back to Anzager to 60 years ago already. Usual derivations, what you can learn from standard references, they go in a rather long way. So first, you represent this dn as a Topliss determinant. Okay, and then you say, wow, I'm an educated guy. I know that Topliss determinants are related to orthogonal polynomials. So there is a big theory of asymptotics of Topliss determinants, which was actually developed by Segyo by request coming from the Ising model. So that's an interesting story. If you want to learn it, just Google the names Segyo, Anzager, and Kakutani. Just Google this triple, and you learn really fascinating story. Okay, but that's a long way. So you start with combinatorics or with some other formalism, maybe with free fermion algebra. Then eventually you get Topliss determinants, and then you say, okay, let us try to understand their asymptotics. What I'm going to present is a shortcut. So this is a shortcut, effectively, of the same story. Okay, how to compute dn. And I'm going to start with the critical case. So dn for x being critical. And you have an exercise to compute dn, okay, the limit of dn's under criticality. So yeah, I'm going to comment on that. Okay, an observation. Let me denote this function somehow. This c is a point on the integer lattice. So I'm going to define this function to notate, to use the notation vks, where k is here, s is there, and what they're of the same parity. Right? This point is 0, 0, and this point is 2, 0 in my notation. So this c is ks. And there is an observation. An observation is the following. Let's try to understand what is the value of my function exactly here. Well, I should put chi c mu v. This is the product of mu and sigma. And when I put two disorders at the same vertex, nothing happens. So what I claim is that this is the expectation of sigma, what's that, like 1/2 0 to n plus 1/2 0. This is the n. Just because of the formalism I introduced. Okay, let me try to think what is the value here. So what is the value at 2n 0? Okay, this disorder survives. Here I had spin multiplied by disorder by the same spin. So spin cancels out. So only mu remains. But then I say, look, but mu mu in the dual picture, this is sigma sigma, right? This is again dn. Just a second. By the way, note that I do not use the fact that at criticality there is only one Gibbs measure. If there were two Gibbs measures, one for plus boundary conditions, the other for minus boundary conditions, this is third. This would be still okay, because the expectations of two spins, of the product of two spins, they're well defined even below criticality. What's what? Dn is just the correlation, yeah, that's the correlation between two sides at n lattice steps. Okay, if you wish, this is a definition. Or that is a definition. So what I use is translation invariance of the measure. Okay. What I use is that they're the same. And now, okay. Yep. U and V are fixed, but they depend on n. So V is minus 1/2 0. Okay, it is independent of n. And U is 2n plus 1/2 0. Okay, like on this picture. So this is V, and this is U. Okay, this is UV, mu V, and this is sigma. Okay. But now look, my function is just harmonic everywhere except these 2 points. So all other points, they are far away from branchings. So everywhere else, I can use this trick. So, okay, by some, well, also to be purely formal, it is a bounded function because all these correlations, they are strictly less than 1. So this is something like a bounded harmonic function except 1 point. Actually, it is slightly more complicated because of the branching, but it even helps. What I want to say is that these values by harmonicity these values define the function uniquely. By harmonicity and boundedness. Define. Like, okay, if there were no branching, there's just a statement. If there is a bounded function which is harmonic everywhere except at a single vertex, it is uniquely defined by the value at this vertex. So, yet again, look at this picture. So here is a corner, right? So the notation is like on this picture. And this mesh is chosen so that the next corner of the same type is 2, 0. So K and S, they're integers of the same parity. Because, okay, I do not have a corner of the same type here. Okay, so that's the notation. So this is 1, 1. And this is 3, 1. Okay, so I restrict attention to corners to just vest corners of my faces. Better? Other questions? No. N is fixed for a while. Okay, locally, not for forever, but for a while, N is fixed. And K and S are just running variables. Are just running variables in this plate. So again, C is just the corner with coordinates KS. That's exactly what's true. Okay. So, and the message to which I'm going to pass in, I don't know, maybe 5 minutes, is that, okay, this function is just a multiple with a factor dn of some very concrete thing, right? We should be able to construct such a function. well, maybe in probabilistic terms, but better in explicit terms. Okay. The only question is, well, but what next? So I have dn. What type of information? Just a second. This gives me, because okay, right now dn figures out as a multiple. No. KNS are not random. I say those are Runyon variables. So those are those are coordinates of a corner. So I think about these expectations as a function of C. Right? So I have collection of, if you wish, random variables indexed by C. U and V are fixed. And I'm thinking about how this expectation depends on C. Yeah, we just move them, I would say. We do not choose them. Yeah, we just move them. Just like think about, I don't know, the green function of a random walk, right? The same idea. So I have some probabilistic quantity attached to, assigned to every vertex, okay, which is a harmonic function for the green function. Okay, so okay, so the idea is that P is the n by something concrete. Okay, concrete in quotes. That's a question how to construct it. But yeah, yet again, how it all, this might help to compute the n. And here is another observation. Okay, what I told on the left is that this discrete harmonicity identity holds everywhere except near the branching, except these points in my concrete example. And I might wonder, what is the mismatch in this identity exactly at these points? And let me, okay, that's the notational question, what is the Laplacian? So for me, the Laplacian will be an analytic Laplacian, somewhere dh delta hc will be some hc plus minus hc. Okay. I grew up in analysis, so if you are more probabilists, it should be other sign, but okay. So another observation is that the value right near corners, right near branching, sorry, can be computed as well. And this is actually minus 1/2 dn plus 1. And obviously, picture is symmetric. Let me try to explain from where it all this happens. When you sum these three terms identities, by the way, it was, I made a mistake. Okay. What's the mistake? Okay, it shouldn't be this two. It should be like this, that, and maybe that's it. Anyway, some finite number of them. On this picture, what happens is that if there is a branching right nearby, I want to keep consistent colors, but that's not easy. If there is a branching right nearby, then when you take a linear combination, this value and that value, they now differ by sign. They do not cancel each other. Just because when you travel on your Perkin lot, multi-level Perkin lot, you're at different levels of this lot. So basically, the mismatch is nothing but the value here. with maybe some multiple. And the value here, yet again, so this is dn plus 1. Why? Because there is mu v by this spin. Mu cancels, so dn plus 1. So this dn plus 1, it comes as an expectation of chi minus 1/2 0 minus 1, sorry, 0. Yeah, well, unfortunately, the life is like that. It is meaningless to derive these equations on the blackboard. So it doesn't help anybody. I tried. So the only way, if you are really interested, you check themselves. If you are not interested, you trust. So that's there is no better option. So these two, they really extremal things. Everything is in between. So yet again, just to emphasize the idea is that here no cancellation happens because of the branching around this point, and the value here is exactly dn plus 1. Yeah, but now we have a wonderful perspective. So if we really are able to construct this function as a concrete function, if we are really able to say that, okay, look, guys, this is a concrete function, then we should be able to compute this Laplacian. And so, okay, this construction of a concrete function, constructing this concrete function, gives n plus 1 over d. That is the whole idea. Now, okay, let me sketch the construction. And yet again, the whole idea of the second set of problems is to do this in a more complicated situation when the model is not self-dual, is to do this under criticality. And this includes some theorems in the theory of orthogonal polynomials, which I might be not familiar with, but there are references, and that's a nice piece of material to learn. Not that much related to the Ising model, but that's just a basic integration. Okay, so how should I construct such a function in my case? The idea is, again, pretty much similar. So I have, at least above the real line, I have an equation which is translationally invariant. So maybe I should do Fourier transform. So just explicit construction. Let me take my notes. So there is some constant to be fixed later. This k plus n is just to make, to shift, so that instead of points 0 and 2n, I have minus n and n. So what I should take the Fourier coefficient of many things, and I'm going to comment on them, obviously, of this function. So what is what? Yet again, the source is the Fourier transform, so basically you should think about this function. So what is this function at the level S? So what I'm doing Fourier transform at every line S constant. Okay, what is what? So this interact T is something very concrete. So something very concrete is is this expression. But what is important, the most important in the whole story, is that this is a solution to the following identity. Y is cosine t 1 plus y squared. 1/2 somewhere. So why this identity? Just think about it. That's exactly harmonicity condition, right? When I'm at the level s, the value, the coefficient in front of exponential I kt should be the mean value. So cosine is what? Is exponential it plus exponential minus it over 2. So this is 1/4 multiplied by 4 terms. And each of the terms exactly gives me one of these C plus minus sharp flat, one of these things. Okay. So this is what guarantees harmonicity. Okay. Now, what is P? Pn is just a polynomial of degree n. But actually, this is not a polynomial. This is the Legendre polynomial. Pn, Legendre polynomial. Pardon? No, just Pnx. Pnx. X from -1 to 1. This is an orthogonal polynomial of degree n with respect to the constant weight on this interval, on this segment. Okay, first of all, why polynomial? Just because by construction, remember my function, it is actually a function on the double cover. And if I think about square root z minus, these functions, well, in fact, because the plane is symmetric, it should vanish on the real line outside of the branchings. Just because I can always flip I can always use upside down symmetry of the plane. And my function is uniquely defined by the values. So this function, okay, y polynomial to vanish on R except VU. Now, why the orthogonality condition? So yet again, what is Legendre polynomial? Legendre polynomial is specified by the condition that the integral Pn x xk vanishes for all k less than n. -1, 1. And this condition can be rewritten in, I can just make a change of coordinates. And here, obviously, I use useful change of coordinates. That's not cosine to k. This is cosine kt because that's a linear combination. Sine t dt. I took an integral over the whole circle. This is why absolute value of sine. Otherwise, it would be integral 0 pi. So what is the source of this condition? In fact, okay, that's to fix all the details is basically the work to be done in the exercises here. That's complicated, well, some interesting derivation. In fact, we do know something more about our function. So the properties we need to fulfill, they are not restricted to harmonicity condition here. We also do know that our function is harmonic, say, at this corner. We also do know that this harmonicity condition holds. And all the values are explicit. So it should be possible to write down what this harmonicity condition means in terms of this polynomial. So that's exactly this one. So yet again, what are the conditions we need to satisfy? We should be harmonic everywhere except these points. The function is symmetric, so we can think only about the half plane plus the real line. Above, this is just a choice of y. On the real line, it should be polynomial just to vanish here and there. And it should be some condition in between the points. That's exactly the condition. So what I claim is that this is an explicit construction. And in this explicit construction, of course, one can compute the Laplacian at this point. So what happens is that at the end of the day, so that's a sketch, not the very full derivation, but I hope that sufficient amount of details is given. So what is the, I should erase something. Yep. What is the the end? What is the conclusion? So, and the conclusion is that, okay, is that the ratio dn plus 1 over dn can be expressed as, okay, some concrete constant depending on n. The norms of orthogonal polynomials on -1, 1. Actually, the value of the Laplacian at this point, this corresponds to k equals n here, and that's morally the norm of Pn. So these things are explicit. Okay. And this leads to the result, which is known under the name, the formula due to TTV. Something very, very concrete. Let me write the final answer. Well, it's not that short, but nevertheless, this is absolutely explicit. Well, this is something that can be written in factorials, effectively. So the most important thing to understand here is just the fact that spin correlations in the Ising model, they are very closely related in this situation, in situations when enough symmetry is present, to orthogonal polynomials. So in this picture, effectively, the values of my function v, they are just coefficients of an orthogonal polynomial, which is there. A rather remarkable fact if you never heard about such a thing. Well, at least I find this remarkable. Okay, what can we benefit from this explicit answer? In particular, we can benefit the asymptotics of this quantity when n grows. So in particular, we can say what happens at large distances. And at large distances, this decays as n minus 1/4. Not visible? No. This is, okay, I wrote 2n because 2n in my notation is the Euclidean distance between them. Okay. This is the case like some numerical constant, and the exponent is 1/4. Okay. Yeah, now I'm going to say what is the conclusion of the exercises. So, okay, just what is the exercises? Again? Well, it depends on the level of terminology you want to use. So how you can view that? You can view it as a discrete Riemann-Hilbert problem, because you can say, okay, I do some cuts, and I replace the saying that my function is defined on a double cover by the saying that this function has this jump on cuts. Just change the sign. Okay? But what I want to emphasize is that everything else is explicit. So you do not need to to formulate anything. So that's just a matter of constructing this concrete function. Like imagine you want to construct the green function of a simple random walk on Z2. That's exercise from probability 1 class or probability 2 class. What you do Fourier transform. Okay, that's just explicit. That's the same level of logic. So I have some function that came to the consideration from probability, and I want to construct it. And then, okay, if you work with more complicated configuration, and this trick with the Fourier transform in this direction is not available, then you are in trouble. Then what you do, you say, okay, I can try to think about my functions as solutions to Riemann-Hilbert problems in discrete, and that's exactly the reason from where Penlevé equations appear, and so on and so forth, if you are familiar with this terminology. Okay, one may, again, come to the error from different points, but okay, that's one of the perspectives. Okay, so what happens below criticality? Below criticality, this is again exercises. Exercises in T2. That's a sequence of 4 problems. The answer is the following. There is no very concrete formula for the n like here, but what you can do, you can study the limit. What happens when 2 spins are far away from each other. And the very concrete answer is here. This limit is just positive, and yet again, what is theta? I can always use the notation x is tangent theta over 2. So this manifests the phase transition because, well, what we see is that for small temperatures, 2 spins being far apart, they still feel each other, so they're positively correlated. And at criticality, this breaks. They start they start decay in a polynomial way, the correlation. So coming back to your question, Leo, well, theoretically, this is a different 1/4. So theoretically, nobody guarantees you that this 1/4 at criticality, which is 1/4 in n, is the same exponent as here, which is the exponent effectively in, well, that's roughly beta minus beta c. Okay, so that's a peculiarity of the Ising model that they can cite. Not going time to comment on that. Okay, so and then the very last remark for on these things is that in principle you might be interested in more complicated setup. For this simple computation to work, what you actually need is only the fact that you have a symmetry in one of the directions. Like you need that these equations, they're the same all the way up and down. So what you need is effectively here is that you can write the answer in this way. So in particular, by this trick, you can analyze what is called layered Ising model when the model is not homogeneous, but constants, they're constant on vertical lines. Okay, as you might guess, this leads to more complicated orthogonal polynomials, to basically to more complicated measures on the unit circle that you might be interested to study, or might be not interested to study. Just to mention is that the whole idea is not restricted to the homogeneous grid, right? So that's just a matter of in which situations we are able to construct this function concretely. And the second comment, actually, it was your question, and I already partially answered. Well, you might have heard, at least some of you, that the spin correlations of the Ising model, that's an object which satisfies many, many identities, differential equations in temperature, and so on and so forth. So I'm going to comment on this right at the beginning of the next lecture. I mean, what is the philosophical reason? But already here, you might see a kind of isomonodromic story, right? Probably you are familiar with that since you're asking about Riemann-Hilbert. That's okay. What we are interested in is like functions with prescribed -1 monodromy around vertices. Okay, that's it. Are there any questions? If no, then let me remind you the plan. So the plan for today is to fix the first exercises set, which is about propagation equation and about this computation. And nope, not about this computation either. Just about propagation equation to be absolutely familiar with what happens. And then the goal for tomorrow, or for those who worked hard and already did the first sheet, is to understand this proof in detail and generalize it below criticality. I mean, just to understand what objects pop up there. Okay.